Thank you very much. Thanks a lot for having me, and very nice to see many so well-known faces and names. So yes, the paper I'm going to present is a joint paper with Gerd Mühlhäuser on smart products, liability, investments in product safety, and the timing of market introduction. And actually, let me mention that right now here at the Center for Interdisciplinary Research in Bielefeld, we have a research group which is going on for a whole year. We focus on legal and economic challenges of smart products. And this paper is kind of in this area. So if you're interested in this group more broadly, I put actually a link to the webpage of the TIF group in the chat. So please let me know if you want to participate in some of the activities. There are still workshops coming, and there will be a closing conference and so on. Or also if you want to come and stay some time here, we also have funds actually to host you. And as Peter says, he is currently here, and Andrea is here, and so it's a very nice and active group. Okay. But so this paper is already finished. It was just recently published in JDC. And so the motivation for the paper is that, as we all know, digitization is a very important phenomenon. There are more and more smart products appearing in all different kind of areas, not only the autonomous driving that we are looking at, but also household appliances, health products, and others. And so one of the properties of these smart products is that they are autonomous. So there is a relatively well-known paper by Porter and Heppelmann on smart products, and they give 4 properties of such products, which is they can collect data, they can to some extent control, they can to some extent optimize, and also at least some of them are autonomous, so they can make autonomous decisions. And here we are focusing on this last property of such products. So in particular, we are focusing on autonomous vehicles. But I mean, that's our main motivation. The model that we develop is, I would say, more general and could also maybe apply to some other autonomous products. Yes, let me also mention, if you have any questions in between, please just interrupt and ask them right away. Okay, so if we think about autonomous vehicles, then in the long run, we might expect that those vehicles will be very safe, that we have fewer accidents than we have now, as cars are still operated by human drivers. But clearly, there is still some development to be done, and till they are fully matured, there will be accidents and damage also caused by these autonomous vehicles. And there is some discussion, I will talk a little bit more about this, who then should be held liable for the resulting damage. So if there is this autonomous car driving around, you're sitting in the car and the car is causing some accident. So who should be liable for that? And currently the standard approach would be that if you are the owner of the car or the driver of the car, you as the one operating this product, you will be liable. That's at least the legal situation in Germany. But now if you're not really driving anymore, but you're just sitting there and so to speak, the decisions are made by this autonomous vehicle, then the question is this still the right way to look at this? Or shouldn't it rather be that the company who produced the car or the company who produced the software which is operating this autonomous car, that these companies should be liable? And there is quite some legal debate about this issue, and also quite some, I should say, public debate. So here we have some relatively recent news on the press about this, or reports in the press, some of them German newspapers, some of them US and English ones. So the main point here always is, okay, what happens if such autonomous products get out of control and to do something that you wouldn't want them to do, and then they cause some damage. Who should be liable for that? And that's the main question we address in this paper. And we want to address this, of course, the different angles from which one could look at this question. But our angle is, I would say, more industrial organization, or I would say economics of innovation angle. So we're trying to understand if we change this liability regime, what will it do to the incentives of the firms who develop such products? So what will it do to their incentives in terms of investing in the safety, or also with respect to the timing of the market introduction? Those are the main questions we want to address. So to do this, we develop a dynamic model, and we have a very simplified setting where essentially the liability regime is characterized by one single parameter, which we will call beta. And the single parameter tells us what is the share of the damage that is covered by the firm, and the remaining share that will be covered by the consumer, by the user. And we want to understand if we change this parameter beta, so this allocation of the damage between the firm and the consumer, what does it do? As I said, to the incentives to invest, to the timing, but also then to the resulting product safety. And this dynamic framework we're developing allows us to actually distinguish those effects on different time ranges. So we can look at what is the implication if we want to understand how safe those products will be in a very short term, but also in the long term. And we do some welfare analysis, and we also then compare different legal rules. So I assume that not everyone here is in the law and econ area, and not maybe fully familiar with the different type of liability rules. I have to admit, I also was not before I was starting to work on this. So what we are going to do is we're going to look at what is called a strict partial liability rule. And what such a rule does is what I just briefly explained. If there is an accident and there is some liability to be allocated, no matter what the safety of this car actually was, a certain fraction of the damage is paid by the firm, and the other fraction is paid by the consumer. Now, if we have a negligence-based rule, that means that there is a certain minimal safety level which is defined. And as long as the company puts a car on the market which does not have the sufficient high safety level according to this rule, then the company is liable because they didn't, so then they are negligent, as one would call it, because they didn't fulfill this negligence standard. But if the product on the market is above this level, then the firm is fine, and any damage would then be covered by the consumer. A little bit more strict version of this negligence-based rule would be what would be called a direct safety regulation, where there is a minimal safety standard, and as long as the product doesn't have this minimal safety standard, it cannot even be sold on the market. So then you need to be above this level in order to sell at all. So this is, as we will see, closely related to the negligence-based rule, but it's slightly different. Okay, so those are the three rules we're looking at, but in particular also in this presentation, I will mainly focus on the first one, what is called the strict partial liability rule. Okay, so what is our contribution, at least in our perception of this paper? The first contribution is that it's actually a dynamic analysis. If we look at the law and economics literature, which in some sense is working a lot with applied microeconomic models, typically this literature relies on non-static analysis. So just having the dynamic framework already, I think, is an innovation to this literature. And also, this allows us to take into account, as I was describing before, some trade-off between short and long-term effects that typically you cannot do if you just rely on a standard kind of more static framework. So doing this, we can identify some, in our opinion, new intertemporal trade-offs and so thereby highlight some implications of different liability schemes that have not been mentioned so far, and I will come back to this. But then we do a calibration of our model, and using this calibration, we can also make some more normative statements about what would be the welfare maximizing liability rule in this framework. And that is also, I would say, a new feature that we have here in our paper. As you will see, the current version of the model still is rather generic. So one could discuss how many of the features of the product we're looking at are really specific for a smart product. But we believe that this framework actually is a very good starting point to also introduce more specific features of smart products, such as interconnectedness, that you can update those products while they're in use, and so on. Okay, now let me give you the main findings. So by the way, I get here from time to time a message that my connection is not very good. I hope you can still hear me well. If you don't, please let me know. Okay. So the main results that we have is first, as I said, we looked at what is called this strict partial liability regime. And there we can see that there are different effects of moving liability from the consumer to the producer. So there is one effect, which I would say is maybe the standard effect that one would also get or one has already observed also in other, for example, static models, which is if I move more liability to the producer, then in the long run, this generates additional incentives for the producer to make the product more safe. And that's maybe what you intuitively would think. If the producer is liable for a larger fraction of the damage this product is generating, the producer has higher incentives to avoid such a damage and will, in the long run, invest more in the safety of the product. That could lead, as we will show, also to kind of what one could call overshooting or so. So if you make this liability too harsh on the producer or too stringent, then it might not be profitable for the producer to develop this product altogether. So if the liability that the producer is facing is too large, then this might forestall the innovation altogether. Which is also a result similar to what has been found in the literature. What is really new, I would say, is the second effect. So if we look at the more short run, then actually moving liability from the consumer to the producer will reduce the safety of the product. So in the short run, you make these products less safe if you put more liability on the producer. And this has to do with something that we call the quantity effect. Which means that if the firm faces stronger liability, it will delay the introduction of the product to the market. It will introduce initially with lower quantities. And given that it will move slower and with lower quantities, this reduces actually the incentives for the firm to make this product safe. So in the short run, we'll have a negative effect on product safety by increasing the liability of the producer. So that's, I would say, maybe the most interesting effect that we identify, and that, as far as we can see, is also new to the literature. So then, as I said, we will calibrate the market, and from the calibration, so we calibrate the model to the US car market. And from this calibration, we get that the liability actually, if you think about welfare maximizing value of this beta parameter, of the parameter allocating the liability. It should stay where it is now, which means fully making the consumer fully liable. So in our standard setting, the welfare maximizing liability scheme is where even though the consumer is not doing anything while driving around in this autonomous car, it would still be optimal to have this consumer fully liable and have no liability for the producer. Now this can change if we use a different liability rules. So then we show that negligence-based rules actually perform better overall than this strict liability. And there you actually do want to have a positive safety standard as a negligence standard for the firm. So that's in a nutshell what we find. And so before I go on to talk a little bit about the model, let me briefly mention the literature. I will not go into the details. So there is literature in law and economics and also in economics of innovation about the effect of product liability more generally on incentives to develop innovations and also to invest in safety. And in this literature, this first trade-off I was mentioning, that if you put too much liability on the potential innovator, this might actually reduce the incentives to innovate. This has been discussed. This is sometimes called the chilling effect of liability on innovation. And there are several papers discussing this both theoretically and also empirically. This is all at least as far as the theory goes static. There are dynamic models, of course, for innovation in investments. List some of them. There are, of course, way more than I list here. But those dynamic models of innovation so far really have not addressed the issue of liability or more generally of the legal or regulatory framework under which these innovations are developed. Now, in the law literature, there is quite active literature, as I mentioned, discussing whether it is appropriate for such autonomous products to have a more stringent liability for the producers. And there is also starting to be a little bit of a literature in law and economics. So is the last bullet. Where, however, so far the literature has focused on slightly different issues than we do here. First, more on negligence-based liability, and second, more on the question how negligence, standards for the effort that the two parties, which here would be the producer and the driver, the level of care these two parties should take, how this should be regulated and influenced by the legal rules. So here the issue is really thinking about the interaction between how careful the driver will be with how good the car is in the end. So this is not what we are talking about here. We will not have any effort or care level or something by the driver. The driver here is in our framework is kind of completely passive. Okay. If there are at this point no questions about the agenda and the overall setting, let me briefly explain the model that we are using. So as I said, it's a relatively simple model. We have a mass one of consumers. Those consumers are non-strategic, so they don't consider whether they want to buy the car today or tomorrow. Each of them will buy one car today. Okay, at each point in time t is continuous time model. At each point in time t, each consumer is buying a car. Now there are two cars available. There is the old product, which is the conventional car. And we don't model the sector offering the conventional car in any detail. We just assume that these cars are sold at marginal cost, which of course is a very strong assumption, but also not a very crucial one. One could relax that. So there is a cost C of producing such a car, and the car, this conventional car, is sold at the price PO, which is equal to this marginal cost C. And all the consumers have the same valuation for this conventional car, which we denote by VO. And this conventional car will give rise to an accident rate alpha O. So we don't distinguish between good and bad drivers and so on. Every driver in our setting is equally good as long as this person is driving him or herself. So that's the, so to speak, the outside option. You can buy just a conventional car. And then there is a monopolistic innovator. And this firm is developing a new smart product, in our case, the autonomous car. And so people are different with respect to the valuations of this AV. So some people really like this autonomous driving. Some people really like to drive themselves. They don't like it. So we assume that this mass of consumers has heterogeneous valuations of driving an AV. And as usual in this type of hoteling type models, we assume it's uniformly distributed on some interval, V lower bar to V upper bar. Now, the autonomous car also has an accident rate. And this accident rate of the autonomous car will change over time. It will change based on some stock variable, which we call the safety stock. So if as a consumer you buy an autonomous vehicle at time tau, then the accident rate of your car for the entire lifetime of the car will be given by alpha of S of tau. So that's an important assumption we're making here that could also be changed. We don't assume that this car can be updated while it's in use. So the safety level that you have when you buy the car is the safety level you will keep as long as you use the car. So this safety level, I will come back to this, will be changed due to investments by the company, by the firm. So the alpha now is the function telling us how the accident rate depends on the safety level. And clearly it's decreasing. So the higher the safety level is, the smaller is the accident rate, and it's also convex. So it's just kind of decreasing, but asymptotically becoming flatter. Now the innovator offers this AV at the price P of T. And if as a consumer you buy this AV, then you will be able to use it for some time. So there is a failure rate of rho, which means the expected lifetime of this AV will be 1 over rho. And then there is a discount rate R for the firm. Okay, so that's the two options the consumer has. The consumer can buy the conventional car or the AV. Now each type of car can generate accidents, and if there is an accident, the damage per accident is some constant D. And now the question is, who is going to be liable for this damage if such accidents occur? Here, as a driver, you are fully liable. So there's no producer liability. So if, as a consumer, you buy the conventional car and you have an accident, you pay D. I will come back whether you can fully cover the D, but in principle, you should pay the full D. Now, if you buy the AV, then, as I said, there could be other liability schemes in place. So for this, we assume that there is what is called a partial strict liability, which means that if there's an accident, the producer will be liable for a share beta of this damage. So the producer will pay beta times D, and the consumer is liable for the remaining share, so 1 minus beta times D. That's what this liability scheme says. And as I said, this beta is in some sense our main parameter we're going to look at, and we're going to analyze what it does if we change this parameter beta. Now, firms are assumed to have D pockets. So this producer, whenever there's a damage, whenever there's an accident, the producer will pay the full share beta times D the producer is liable for. But for the consumers, that's maybe a strong assumption. So there are different reasons. There's also some literature on this, why consumers don't have such deep pockets. It might not actually be able to pay everything that they're liable for. So that might be because they have wealth constraints. That might be if they have some insurances that that's actually deductible of the insurance. Or it might also be some kind of behavioral effect there that they don't anticipate to be able to pay everything. So
May I ask a question, Herbert?
Sure.
So for the normal car, old car, consumer is assumed to be able to pay D, but not for the new car.
No. In any case, so what I was describing so far is the damage the consumer is liable for. So the consumer is liable for the entire D if he's driving a normal car, and 1 minus beta D if he's driving an AV. But then the consumers evaluate this liability, whether it's D or 1 minus beta D. We're using a function which we call K, which is a concave function which at 0 has a slope of 1. So for the first euro you pay in full, but then this is a concave function, so then the slope becomes smaller than 1. And
I got it. Thank you. Sorry for the interruption.
And so what is important to realize is that by doing this, if the consumer is liable, at least for parts of the damage, then this will generate some externality on a third party, which maybe is the victim of the damage, because it will not be fully covered. But it's so then of the total accidents costs. And for the conventional car, there is always some externality arising from an accident. Okay, so the consumer is evaluating this with a K of D or K of 1 minus beta times D, depending on which type of car the consumer is buying. So, and then we can calculate for each type of consumer. So the type of the consumer is determined by the valuation for the AV, which means the expected lifetime utility for a conventional car is the same for every consumer, and it's just this integral here. So it's R plus rho, because R is discount rate, rho is the rate with which the car breaks down. And then we have, this is the flow of the utility you have from using it, and this is the rate with which you have an accident. And if you have an accident, you have to cover K of D, okay? From this, we have to subtract the price, which is for the conventional car, remember, that's just the marginal cost. So this is giving us the expected utility UO if a consumer decides to buy the conventional car, and then we can do the same expected utility calculation if the consumer decides to buy an AV. And here we can see that there is this liability term, which is the rate with which the accident will occur. And then we have the K of 1 minus beta times D. And the VI here, as I said, is heterogeneous across consumers. Okay, so and then it's very simple, like in the standard totaling model, the consumer will buy the AV if the utility of doing that is larger than the utility from buying the conventional car. And this gives rise to a demand curve for the AV. One thing to realize is that this parameter beta, so the liability parameter, it does influence demand because, as formally we can see it here, if the beta goes up, so if more of the damage is covered by the producer, then it means less has to be covered by the consumer, and that increases the willingness to pay by the consumer. So a change in beta will actually shift the demand curve for the AV. and that's important. Let me also mention it more as a technical side remark. If we would assume that consumers also have deep pockets, so if there would be no such concave function K determining the evaluation of the liability by the consumer, then actually the beta would, in terms of the quantity that's sold on the market, would completely cancel out. Because if you shift liability, the price would change one-to-one, so to speak, proportional to this shift. And in the end, this will completely cancel out. If you increase the beta, then the price will change, but also the willingness to pay will change, and the quantity will still stay the same. So the fact that the beta here has an impact on the demand depends actually on this fact that the consumers, differently from the firm, doesn't have deep pockets. Okay, now what does the firm do? The firm can build up the safety stock of these cars by investing. So that's a very standard investment model here. X of T is the investment of the firm in increasing the safety stock. So S dot is just this investment minus some depreciation term delta times S. And we assume also, again, very standard, that we have quadratic cost of investment, and we scale this cost function by this parameter data. So if data becomes small, it means the cost becomes small, but also marginal costs become small. So from that, it's clear if one thinks about the problem, that now the innovator, our firm, for a given safety stock S, can determine what is the optimal price, the monopoly price, which is a very standard expression. I didn't put it on the slides. And from this monopoly price, then there will be some quantity, Q. So we have a P star as the monopoly price, a Q star as the monopoly quantity for a given S. And this, of course, will give rise to a profit the firm is making, and that will be an increasing function of the S, so of the safety stock. In particular, there will be some minimal safety stock, S, or S lower bar, such that the firm will put the car on the market once the safety stock is above S lower bar of beta. And so that's the lowest safety stock, such that by charging the monopoly price, the firm can actually make a profit. Okay, so that's what is happening every period T. So the setting of the price, as usual in such models, does not have any intertemporal implications. So we can just assume that every period the monopoly price is set, which means that the only variable which has an intertemporal, or the only control variable which has an intertemporal implication is this investment X. So in the end, we obtain a control problem for the firm where the only control is this X, so the investment. And so the firm tries to maximize this expression here, which is so the quantity times price minus cost. So then this here, this integral here, is the expected liability cost of the firm, yes, per car the firm is selling. So this expected liability is I sell the car at time t, and then there is the safety stock S of t. So then for the rest of the life, this car will have an accident rate of alpha of ST. And then whenever there's an accident, as a company, I'm covering beta times t, all right? So this is just the expected revenue, taking into account expected future liability costs. And then from this, we subtract the investment cost H of X. Okay, so that's the problem the firm is facing. And in the end, this is a relatively standard dynamic optimization problem. And we can get some insights on the optimal investment function using both control theory and dynamic programming. And actually, in this paper, we even use both for different purposes. Okay, so if we look at this problem, the first thing to realize is that if we look at the optimal investment and on the dynamics of the safety stock under optimal investment, we might have two types of steady states. We might have active, what we call an active steady state. So that's a steady state where there is a positive safety stock, and where in the long run, a positive quantity of these AVs are sold. So that means that's a scenario where the autonomous vehicle is developed and then put on the market and sold in the long run. And then there is what we call a passive steady state, which is a kind of a steady state on the boundary where the safety stock is zero. And then, of course, with zero safety stock, nothing is sold. Also, the firm is not investing anything. So then that's a situation where the firm just decides it's not worth it and is not developing this AV and is never putting it on the market, which is quite standard and is to show that every optimal path converges to one of those two steady states. So either we get or we don't get this development. And in our analysis now, we focus on initial condition where initially the safety stock is zero, which is essentially just a matter of normalization. So we call the initial safety stock zero. And then we not very get a result, which is not very surprising, but still maybe interesting. So if we vary this cost parameter data, so remember the data is the parameter which is scaling our investment cost function. So if the data is very small, so investment costs are very low, then no matter what the liability scheme is, the product is always developed. So we always have convergence to an active steady state. If, on the other hand, investment costs are too high, so there is an upper threshold data bar, such that if the data is larger than this, then no matter how you distribute the liability between consumers and producers, the investment costs, development costs are just too high, so it will never be developed. Those are not very interesting cases. So the interesting case, of course, is the one in between, where if the data is between those two thresholds, and then we can indeed show that then it depends on the liability scheme whether the active or the passive steady state is reached. So there is some threshold, beta hat, and as long as the liability the firm faces is below this beta hat, then the firm will develop the product. But if the liability is above this, then it will not. So this is yes, one could translate it. We don't do it because we don't look really at the state space here, but of course, in some sense, it's related to the fact that we have some schema point here. And this is exactly when the schema point hits the initial condition zero. That's when we get this threshold beta hat. Okay, so that we can show generally without doing any calibration. But now what we are more interested in is to understand the properties of the actual dynamics that emerges under different beta values. And for this, we rely on numerical results. So we did a relatively extensive calibration of the model using all kinds of data sources from the US with the reference year 2017. And doing this, we get actually a quite nice calibration where also some of the targets are hit very well. But I'm not going to go into this calibration here, but just show you what happens now if we use this parameterization that we derived from this calibration. So now, again, we're looking at what happens if this liability parameter beta becomes larger. So here we have two pictures. The one on the left tells us what's happening in the long run, and that's just confirming the analytical result I was just showing. So here we look at the steady state, and as the beta goes up, and we look at the safety stock in the steady state, then the safety stock actually goes up. So that seems to do what it should do. If I move liability to the producer, In the long run, those cars become safer. But if I do too much of that, if the beta crosses the beta head, then all of a sudden the passive steady state becomes the stable, or let's put it differently, the initial condition moves into the basin of attraction of the passive steady state. So, and then this firm doesn't develop the product. Okay, so if there is too much liability, then the product is not developed. Okay, so this is just, as I said, more or less confirming what we found analytically. Now, what I want to focus more on in the next few slides is the dynamics. And so here on the right-hand side, we see the time under the optimal investment function to reach the accident rate of the conventional car. Yeah, so what we see here is on the horizontal axis, this parameter beta, the liability parameter. On the vertical axis, that's the time that's needed to make this AV as safe as the conventional car. And we can see this time is actually increasing with respect to the beta. So the more liability I put on the producer, the longer it takes for the producer to make the car as safe as the conventional car. And so here we already see this kind of dynamic trade-off. So here, the moving liability to the producer doesn't do what one would maybe want it to do, which is make the car safer, because it seems to take much longer to make the car even as safe as the conventional car. And this can be understood by looking at the dynamics of quantity and investments. So here we can see the quantity of AV sold on the market for different values of this liability parameters. Black is if all liability is with the consumer, blue is that there is 15% with the producer, and red is 29%. So why is it 29%? Because 29% for this calibration is exactly our beta head. So if I would move the beta above 29%, then our producer wouldn't even develop this AV. So with 29%, the producer does develop the AV, but if we look at the dynamics of the quantity, we realize this shifting the liability to the producer leads to a delayed introduction into the market. And throughout, we see lower quantities of the AVs on the street compared to scenarios where there is less liability with the producer. Okay, this of course has to do with the pricing. So since as we move up the beta, the firm has higher costs. This will also drive up the prices. At the same time, also the willingness to pay for consumers goes up, which also drives up the pricing. So the price here goes up, and this price effect is dominating. So the quantity becomes smaller. And now the fact that the firm is selling less and it's selling later reduces the incentives to invest in safety, because safety is only profitable. So increasing the safety is only profitable for the firm if the firm sells a car. And so the fewer car the firm sells, the lower are the incentives to invest in increase of the safety. So that's very similar to the logic that we typically have in process innovation models. And so we can see that initially, so here on the left-hand side, we see the investment pattern for different values of this liability parameter. Initially, the investment into the safety stock is much lower if a lot of liability is with the firm. So initially we have exactly this effect that because the quantities that the firm will sell in the near future are much smaller, the firm has lower incentives to invest. And then in the long run, this turns around. So as we have seen here, the quantity differences in these three scenarios become smaller over time. And although even in the long run, less is sold under a higher beta, this effect becomes smaller. And then the second effect dominates, and the second effect is the effect that we know from the static models. If I'm more liable, then I have stronger incentives to invest in the safety per car I'm selling. So here in the end, this is the dominant effect, but initially the quantity effect is the dominant effect. And that implies that, as you can see on the right-hand side, in the short run, actually the safety stock of this car is much lower if there is more liability on the firm side compared to the consumer side. So that's the intuition for this. And okay, here I have a slide for the intuition, but I will skip that. And putting this together, we can get this figure here, in particular the figure on the right on this slide, which gives us the accident rates depending on the beta. So these are different types of accident rates. So here the solid line on the top, that's the accident rate at the time of market entry. So that's how large the accident rate is when the AV is brought to the market. And we can see, well, the larger the beta is, the safer the car will be when it comes to the market. So that's okay. That's also very intuitive. But as we can see on the left-hand side, it also means that the market entry time is really increasing quite steeply with the beta. Okay, so it will come at a higher safety, but much, much later. And that implies that if I look at the safety of the car at a given time, which is this dashed line here. So here we fix some time t tilde and we ask how safe is this car at time t tilde? And here we can see, as we increase the beta, the accident rate actually goes up. So if I ask the question, how safe will this AV be 10 years from now? Then the answer is, well, the more liability I put on the producer, the less safe it will be. And that's, of course, completely the opposite from what we see in the steady state, which is this lowest line here, where we know in the long run, then putting more liability on the firm will actually make the car safer. But maybe what, as a regulator, we care more about is this more short-run consideration of the safety at some given point in time in the relatively near future. Okay, so this is here the main result we have. And now we can try to understand from a more normative perspective, how would we want to have the data in order to maximize welfare. So to do this, we look at the kind of standard welfare function. We have also, there is a monopoly distortion already, but that's not really very interesting for us. What we are more interested in is the distortion of the safety investment. And here one can see that from a welfare perspective, the firm is investing too little in the safety stock, which is also a relatively common result in these types of models. So we have underinvestment of this monopolistic producer and also underproduction. And given that, now one can ask, so if we want to choose a beta value, so allocation of liability between the consumer and the producer such that welfare is maximized, how should we do it? And the answer is, as one can see here on the right-hand side, if we look at the total discounted welfare generated on this market, then the best thing to do is actually to have a beta of 0, which means keep all the liability with the consumer. And intuitively, now that we have seen what's going on, I think it's maybe quite intuitive because this quantity effect I was mentioning, so the fact that if the beta goes up, the quantity that is sold in the early stages of this market development is much smaller. This is very costly in terms of welfare, because from the welfare perspective, too few units of this product are already sold. So that's the dominating effect, and that effect implies that we should have a beta of 0. Okay, clearly, I should say that this is due to our calibration, but we also did quite a bit of robustness checks for this. That seems to be a relatively robust result in our setting, that if we have strict partial liability, in terms of welfare, we want the liability on the side of the consumer. But we can actually do better than that, also in terms of welfare. And the way to do better than that is not to have this very simple strict liability regime, but to use negligence-based liability. So the way we model here the negligence-based liability is that we say, okay, there is the regulator is fixing some negligence standard as neg. So that's given. And then we make a pretty strong assumption, which is the safety standard of the car can be verified in front of a court of law or whatever, which means that whether the firm is liable or not can depend on the fact whether the safety standard of the car is actually above or below this negligence standard. And the assumption here is if the safety standard, so the safety stock of the car is below the negligence standard, then the firm is liable. And if the safety standard is above this negligence standard, then the firm is not liable, which then means that the consumer is liable. Okay. And now one can try to analyze what this will do to the incentives of the firm. And I will maybe not go too much into the detail there. So one thing to realize is that there are essentially three scenarios with respect to the timing of the market introduction. And that's what is given here at the bottom of the slide. So it can be that the negligence standard in some sense is irrelevant. So if the negligence standard is so low that even if there would be no such standard, so if the firm would never be liable, the firm wouldn't even want to introduce the car at such a low safety, then there is negligence standard, but in some sense it doesn't matter. Now, if the negligence standard is above that, which means that at the point where the firm without any negligence-based liability would want to introduce the product to the market, but at that point it would still be fully liable because it's still below the negligence standard. So if that's the scenario, then what the firm should do, it should just wait till the safety has reached the negligence standard and it will introduce the product then. But then there can also be a scenario where the negligence standard is so strong that even if the firm would be fully liable, it would introduce the car already before this negligence standard is reached. And in such a situation, as we will see in a minute, I think I'm running a little bit out of time, but if I have 3 more minutes, I can briefly show it. We'll see that then the firm will introduce the AV actually at a point in time where it's still fully liable. So it will accept the full liability and introduce it. Okay. Now, one big difference, and that's what we can see on this figure here, between a negligence standard and the strict liability regime is that the negligence standard actually increases the incentives of the firm to invest early, because the firm now wants to reach the negligence standard as fast as possible. Well, as fast as possible is maybe not correct, because of course it could do it even faster than that, but that would be very costly. So given into account the complex costs, the firm wants to really speed up the initial investment in order to reach the safety standard that's needed for the negligence rule. And that's very different because the larger you put the standard, so the higher you put the necessary safety level to reach the standard, the longer will the firm invest a lot. And that's what we can see here. So in the blue one, that's the less stringent negligence standard. The red one is a little bit more stringent, and the green one is the most stringent one. And we can see that differently from the strict liability, we're making the standard more stringent means that the firm invests less and less in the early stages. Here, it means that the firm is investing more and more in the early stages the more stringent the liability standard is. So in that sense, negligence is really different from strict liability. And that makes negligence actually more attractive. And that's maybe the last thing I'm going to show, which we can see here. So here again, we look at welfare. And the zero here would be the same solution that we get if we have a strict liability with a standard of zero. So with a beta of zero. So if this is just the consumer is fully liable always. That's the 0 point here. And then as we go to the right, it means that we have a negligence standard that becomes relevant. It becomes higher, so it becomes more and more stringent. And here we can see that we can improve with a negligence-based liability rule relative to the scenario where the consumer is fully liable and get a higher welfare here. So that in some sense is the better way to regulate. And also we can see on the left-hand side, which is the analogon to the picture I was showing you before, that now as the standard becomes more and more stringent, not only the accident rate at market introduction goes down, but also the accident rate at a given point in time t tilde now goes down. So here making the standard more stringent actually has the effect, no matter whether you look at the accident rate in the short or in the long run. Okay, that's it. So the conclusions, what we find is shifting too much liability to producers can first render the development unprofitable. But even if it is profitable, if we use strict liability, it will delay market introduction. It will also delay, in some sense, investment into building up the safety stock. So there is really a trade-off between the short-term and the long-term effect if we use strict liability. And this trade-off is not really there if we use negligence-based liability, where we have considered it here. So there are, of course, many extensions than what Luca has. I'm listing some of them here. We could have learning curve effects, which seem to be very relevant for this type of products. We, of course, should have competition. So not having only a monopolist, but having competing potential innovators. And also we might have strategic consumers, because clearly people, when buying a car, maybe act strategically and intertemporally optimal, to some extent at least. But that, of course, will make the model much, much more challenging compared to what it is now. Okay, thank you very much.